días.
Buenos días, profe.
Número 1 esta mañana.
Hoy sí estaba de madrugada. Está
Ajá,
despejadísimo.
sí. ¿Tú desde dónde estás recibiendo la señal?
Yo de Ibarra. O sea, de
Desde
Ibarra
Ibarra
por
también.
el... Sí, por el sur más o menos.
Ujú.
¿Y en qué sector está usted, profe?
Yo estoy aquí al pie de la Imbabura, en la Atahualpa, Alta Atahualpa, cerca de
Ah,
Caranqui, ¿qué? Caranqui, sí. Sí. Las cuatro esquinas.
ya, ya. Ya, ya. Yo estoy cerquita también.
Ajá,
Unas, ¿qué? 5 cuadras, no, menos, 4 cuadras de las cuatro esquinas, para en
ajá,
dirección oeste.
ya. ¿Pero tú eres de Ibarra o te
Sí, yo
quedaste
soy
por
de
aquí?
aquí.
Ajá.
Sí, yo soy de aquí de Ibarra.
Ujú. Buenos días, María Paula.
Buenos días.
María Paula, si recibiste mi respuesta a tu email de Sólidos 2.
Sí, profesor, ya la revisé.
Ajá, perfecto. Vamos a esperar unos minutos, que este curso es grande, pero poca gente esta mañana. Buenos días, Santiago.
Profe,
Buenos días. Ajá, sí.
¿y usted qué opina? ¿Cree que el siguiente semestre ya se vuelva a la normalidad las clases o también será que un semestre más estaremos así online?
A mi impresión es que por lo menos el verano seguiremos online, ¿no? Eh, Sobre todo por la complejidad de repatriar a muchos estudiantes de una zona a otra del país, ¿no? Que pueden tener situaciones distintas desde el punto de vista de la epidemia. Eh, sí, yo creo que por lo menos el verano y quizás entonces el siguiente semestre, contemplando la prolongación que va a tener este de por lo menos un mes adicional, de ver de cómo es el calendario que tengamos para el segundo semestre. También tenemos pendiente de si vamos a hacer las prácticas de laboratorio y obviamente las salidas de campo tendrán que pautarse en algún momento del año, ¿no? Para cerrar este semestre para todas las materias.
Profe,
Eh,
una duda.
sí.
¿Y las horas preprofesionales o con la comunidad, cómo se van a poder hacer en para los que ya están, digamos, en octavo semestre como nosotros? Por ejemplo, yo
Sí,
hay un proyecto que son las vacaciones, pero bueno, ya no creo que se pueda hacer eso.
claro. Sí, sí, hay algunas prácticas que se pueden hacer, prácticas preprofesionales por ejemplo, tuvimos ese lanzamiento de posiciones para asistir en cursos del semestre, eso están dando y eso está generando las bitácoras este, desde el punto obviamente, de prácticas en otras universidades o también, por ejemplo, proyectos de investigación, eso sí también se puede hacer en la medida de que sean, por ejemplo, proyectos que no involucren trabajo de laboratorio, toda la parte teórica sí vamos a poder hacerlo bien, ¿no?
Y la parte eh, ¿cómo
De
se llama? Con la
vinculación.
comunidad.
Sí, vinculación. Entonces, había una exploración que estábamos haciendo en la medida en que esas actividades se pudieran llevar a cabo con investigación, por ejemplo, en casa, y comunicándose con la comunidad vía estos medios virtuales. Hace un par de días, o un día, 1 o 2 días, recibimos unos lineamientos de la comisión gestora al respecto de cómo estas cosas se podían hacer. Entonces estamos analizando a ver porque digamos, la mayor parte de los proyectos de vinculación tienen que ver con investigación ahorita. Tenemos el Inspiratón, que obviamente, digamos, ya las escuelas han implementado eh, modalidades virtuales para impartir esas cosas. Eso debería averiguar cómo es que se está planificando hacer ahorita, ¿no? Por ejemplo, hay ciertos casos que están que tenían, por ejemplo, críticos que tenían que terminar esas horas de vinculación ahorita en el 10º semestre. Entonces, se está viendo cómo algunos proyectos se pueden hacer, otros no. Entonces, deberíamos tener un pronunciamiento oficial sobre eso pronto, con los lineamientos que nos dieron de la comisión gestora hace unos días. Quedo pendiente de averiguar esas cosas.
Gracias, profe.
Chévere. Bueno, creo que tenemos quórum ahora. Entonces vamos a comenzar. Okay, so let me recap a bit on where we were, and so we can continue to advance. So we were studying non-equilibrium carriers. Okay, so we're basically analyzing the situation where we generate excess carriers, as we were calling them, okay? Excess carriers beyond those determined by equilibrium. Okay, so those are carriers generated by, for example, local temperature, local temperatures, external perturbations, external photonic perturbations. Okay, and any other source, local electric fields, any other source of perturbations that made transitions, made for transitions of electrons from the valence band to the conduction band. Okay, so we're generating holes in the valence band and electrons beyond, okay, beyond N0 for the conduction band and P0, okay, for the valence band. Okay, so we always assuming that we have delta N, whatever negative charges are being generated in the conduction band are going to be equal to the number of carriers, number of positive carriers in the valence band. Okay, although these intuitively, of course, if you have an external applied electric field, these charges are then going to move and they're going to distribute themselves in a different fashion in space and time. Okay, but this is an additional assumption we're going to make, is that as any negative carriers that are generated, okay, for example, if you apply an external electric field, okay, are going to move in principle in opposite directions. So this is an electric field, and the positive charges are going to move with the field, and negative charges are going to move in the opposite direction. So this will generate a dipole, okay, or an internal, okay, these generate an internal electric field, which tends to move these charges together. So you generate an electric field, and this electric field does not allow for these charges to separate further, so they tend to move together. Okay, makes charges move together. Okay, and so this sort of generates what is called ambipolar transport. Okay, So this is a charges moving, positive and negative charges move together, and this so generates a condition in the equations of motion of the excess carriers that makes the positive and negative charges move together. Okay, so we had derived a set of equations, okay, that implying this condition of positive and negative moving together. Then we had a set of equations of this form where we had d prime, second derivative, partial derivative of delta n squared plus an effective mobility times the applied external electric field, okay, the n x, and then we had a generation rate of these excess carriers minus a recombination rate, okay, was equal to the first derivative of time, okay? And we always refer here to the negative charges, for example, because there's whatever delta n is doing is being done by delta p according to the ambipolar condition, the ambipolar transport condition, okay? So these d prime, the diffusion constant, was a particular combination of the equilibrium mobilities and diffusion constants, and it was of course a combination of the positive mobilities and the charge densities for each of the species and the diffusion constants, okay? So we have mu n plus mu p. And also for the mobility, we had an equivalent relationship or a corresponding relationship, which was now a function also of mobilities associated and the corresponding charge densities, non-equilibrium. Remember that. Let me finish here. Okay, so remember that for the notation, P and N are the total, okay, total densities. Okay, so N was going to be a function of the equilibrium charge density plus the excess charge density, and also the relationship for P was P0 plus delta P. These two quantities are the same. The excess amounts of the excess number densities are the same, but as we can have either an N or a P semiconductor, then this total charge densities are going to be different, okay? So the condition is applied, the ambipolar condition is applied to the excess amounts, but not to the total amounts. Okay, so we had that equation, and now we applied a useful condition, and generically, so we apply the condition of, we just for practical purpose, we apply the low injection condition, okay, to these equations. And this low injection condition is that delta n, okay, referring again to just a single species, is going to be much smaller, than either P0 or N0, okay? For the case of a P-type, okay, or N-type semiconductor, okay? And of course, for a P-type, then we also had that P0 is going to be much larger than N0, and for an N-type, we're going to have that N0 is much larger than P0. Okay, so we apply these conditions, low injection conditions, which we can apply generically to a practical situation, and we were able to simplify the diffusion constant. Okay, so we had, for example, I'm just doing this limit for the diffusion constant and then write it for the mobility. Okay, so we could write the d prime as a function of n, as n0 plus delta n. Okay, so let's apply it for a p-type. Okay, the p-type limit, and the other limit is equally easy. So we had this just developing the meaning for the total density of negative carriers and positive charges. We have this situation here, and we have N0 delta n plus dp, okay, p0 plus delta n, okay, and now we can take the p-type, right? Okay, so we can take now that delta n is going to, if this is a p-type, p0 is the greatest carrier concentration, so delta n is going to be much smaller than p0, and also n0 is going to be much smaller than p0, so we just get the limit in which dp dn times dp times p0 in the numerator, and then the same thing here in the denominator. The diffusion constants for positive and negative carriers may be a little different, but the difference between P0 and N0 is going to be many orders of magnitude. So again, we're going to get here the dP times P0 here. And if we eliminate now these two factors in the numerator and the denominator, we get now the dn, that d prime, the effective diffusion constant for the excess carriers, okay, for a p-type semiconductor, is going to be associated with the opposite, the sign carriers, okay? So this is going to be the minority carriers, okay? Minority diffusion constant. Okay, so this is a very emblematic result. One of the things that we solved, or that the low injection condition addresses, is that, notice that this is a mu, d prime and mu prime are going to be functions of nu and p, and thus functions of delta n. So if you go back to this equation, we have this is a function of delta n times the delta n in the differential equation, ended up being a nonlinear differential equation. So this is much more difficult to address. So one of the simplifying assumptions we make with the injection condition is that now the d prime and mu prime are no longer functions of delta n. So we end up with a linear equation to solve. Okay, so that's an alleviating factor associated with a physical condition that we generally are going to find in these systems. So we get, we can substitute these d prime, and in the case of the mobility, we get an analogous expression where for a p-type, again, p-type semiconductor, we get that mu prime is going to be the minority carrier mobility. Okay, so we can just substitute those two equations, and for a p-type extrinsic, okay, this is redundant, so if it's p-type, okay, semiconductor, it should be extrinsic because it means that we have to add impurities to it. So we get now the diffusion equation that we are going to use, which is the has space and time still. Okay, so we have the second derivative plus mu n. So we have the minority for the p-type, okay, times the electric field times the first derivative with respect to space, and then we have the generation rate, the recombination rate, and we have delta n delta t. Okay, so perfect. These are the equations of motion that we're now going to address. It's very easy to write for the n-type. We just make we're going to just substitute here in the coefficients the minority carrier, which will be the p's. Then there's going to be some changes in sign because for the n-type, okay, just as a note, so for n-type semiconductors, so that when we make the substitutions in the exercises we're going to do, then we have that d prime is equal to dp, but we're going to have that the mu prime is going to be minus mu p. Okay, so this is an additional problem that if it's not in the homework, please do it, okay, from the previous equations, and include it as part of the problems that you turn in for the next homework, okay, we're going to have. Okay, any questions up to here? So this is just a review. Okay, so okay, so basically from the mathematical point of view is we're going to have to address the solutions to this second order differential equation as the equations of motion depending on the type of semiconductor we're going to have, okay, and the external situation where we are addressing, okay. So we had also seen some qualitative features of what is called the first experimental verification of this formula, of this equation of motion, verification. Okay, which was the Haynes-Shockley. Haynes. Okay, experiment. Okay, and of course here we're going to address it just from the point of view of the theory. Okay, so the Haynes-Shockley experiment was basically this setup here. Okay, so we have a chunk of material, either p-type, okay, p-type or n-type, okay, and you had some electrode here, okay, you had some electrodes. Okay, and we applied an external electric field, okay, between these plates. So we have an external electric field here, and so we introduce at a certain point, okay, excess carriers here. For example, we apply a voltage locally, excess carriers, okay, and we probe the number density of carriers we have with another probe that we can move around in the material. Okay, so you generate a spike here. For example, let me draw it here, like a spike.
Sorry.
Yes?
What exactly do you mean by probe?
Probe is just I just put a voltage. For example, I probe the voltage. So I have some multimeter here. Okay, so I just have a cable with a point, literally like an arrow, and we try to see the changes in voltage, the local changes in voltage here in the material as a function of time and space. Okay, so space, I move the probe. Okay, so the probe is just going to be a contact. Okay, contact, a metallic contact on a semiconductor. Okay, and I just that probe looks for voltage variations. Okay, so maybe next class we can draw a circuit. But although I mean this is one of the experiments that Werner wanted to illustrate in the course. Okay, maybe one of the things we're discussing, that maybe the professors could go in an organized fashion to the labs in the university and sort of transmit their the experiments in demonstration mode to you from the university, and as long as they maintain the the security measures that they should. Okay, so maybe we'll do it. We will be doing that in the next few weeks, so that we can sort of close the semester with demonstrations, at least for the courses that are that lend themselves to this. We can do this maybe in the semiconductor school. So we have a probe, and this probe is going to look at the voltage, the local voltage produced at a certain point in space and as a function of time. So we produce here a pulse of excess carriers, okay? And this is very peaked, for example, depending. And this is done the same way here. So we apply a contact here at a certain point, and then we can see how this pulse is changing as a function of time, okay, and space, okay. And if we fix the probe here, we're going to see first the tail of this distribution, okay. And as we apply an electric field and we have ambipolar, this ambipolar transport, you're going to see this pulse of excess carrier move, for example, in the positive electric field direction, and we're going to be able to see, okay. So now we have some kind of a screen here, okay. So you can see the pulse develop as a function of time. And, this can be, for example, the time variable. So you can see first the leg, and then you see the peak going, and then the other tail of the distribution. So this is a way of probing whether these ambipolar transport equations are going to be working. So we know for example, the variables here. We know the minority and majority mobilities associated with that semiconductor, and so we know all these things here, and we're going to, for example, see the parameters associated with the generation, and which is how we perturb the system, and then the generation rate. So this will be associated with this injection of carriers, and then the recombination rate is going to be associated with the characteristics of the semiconductors to some, for example, delta n over tau, some characteristic time associated with the recombination rate, and we're going to see that in this class also. And what else? And the mobilities are going to, and the diffusion constants are going to be intrinsic quantities associated with the semiconductor. Okay, so those will be quantities associated with. I haven't said what type of semiconductor this is, but we know, for example, it was a p-type semiconductor, then we would be worried about the minorities, minority mobility, and diffusion constant. Okay. So this is the sort of the experimental setup for this, and so we want to address from the mathematical point of view this problem. Okay, so let's set up everything in the differential equation so that we have for example, an n-type, okay, a equation of motion. Okay, for n-type. Okay, for the Haynes-Shockley. Okay, so if we have an n-type, let me underline this so that we know. So we have to write the correct differential equation. So we know we have to write the equation that involves the minority diffusion constant, and we would have this equation here. Okay, minus mu p, and then E0 partial delta n delta x. So we have applied an external field for the Haynes-Shockley setup, and then we're going to have a generation rate, okay, and we're going to have also a recombination rate that we describe like this, okay, and then the time derivative. Okay, so in this setup, then we want to describe, so we inject at a certain point, so we only have generation in a certain point in space, okay? So we inject a number of excess carriers, and so we have the carriers distributed in a certain, at time equals to 0, okay? So at time equals to 0, we inject carriers, okay? Negative carriers, for example, and the corresponding positive carriers will be also generated by the condition, this ambipolar condition. So we inject carriers, and then, okay, we turn off, okay, the injection. For t greater than 0. Okay, so the differential equation, then we have to, for time for t greater than 0, then we eliminate, let me put the condition here, so we eliminate this generation rate for t greater than 0. So we have a spike at t equals to 0. We eliminate this generation rate for t greater than 0, and we are only left then with the second derivative, the first derivative in space, and then we have this recombination rate, which is going to operate all the time. For the time greater than 0, it's going to operate. Okay. Okay, so let's solve then. We have a finite electric field, and so let's solve this equation for time greater than 0. So the solution would be that delta n is going to have the general form n of x and t times some exponential, and we'll see a simpler situation. So this will be sort of the most general situation for a pulse of carriers being injected into the system, okay? And we have the times this exponential here, okay? So we learned a bunch of ways to solve this second order differential equation, and we'll address those solutions in more detail in another class. But we want to get a feel for what's going on. So we substitute this solution here into the differential equation, and we get this a little simpler equation here. Okay, so you just substitute there, you'll get from all this time dependence here is going to be factored out from each of these terms, so we can just get except for this term where we'll get to non-trivial terms. So let me just write that particular derivative down here. So we get delta n, delta t is going to be so at the exponential of minus t over t0, okay, dn prime dt, okay, and then we get minus 1 over tau p n prime exponential of t over tau p. Okay, so this is the only non-trivial from here. There's no just there will be just a product here. Here we'll have take out the time dependence, and here we'll conserve the spatial dependence. The same we do for the second derivative, and so we can write the following equations. We have second derivative n prime for the spatial second derivative minus mu p. Then we have the external electric field, and we have n prime dx. Okay, and this will be equal to the n prime dt. Okay, the extra term I have here will cancel with this term here. Okay, because there will be the product of this. This will be, okay, delta n. Okay, so we have delta n 1 over p. So we have the minus sign. So these cancel them on the right hand side of the equation. So we get just this this equation for n prime. Okay. The solution to this second order differential equation, again, we have both time and space and time. One second, let me plug in my computer here. Okay, so the solution to that differential equation is going to be sort of the most complicated form that's going to be solution to this equation is going to be of this form. Okay, and in the practice session, we should address this so we brush up on our differential equation. A solution. This will be dp times t square root. This is going to be the prefactor of a Gaussian, and then the Gaussian factor here, which is mu p e 0 times t squared over 4d dp t. Okay. And then if we have n prime, we can write the full solution for delta n as n prime times the exponential of minus t over tau. And so we, in addition to this time dependence here, we're going to have the exponential tau p, okay, over this, the time dependence of the prefactor of the Gaussian, okay, square root. And then we're going to have minus x mu p e0 t squared over 4 okay. As I mentioned previously, the form of the Gaussian here has Gaussian. This has a Gaussian form. Okay, Gaussian form. So it's always very useful to remember the general form of a Gaussian. So we have a minus sign. The general form of a Gaussian is going to be something like this, okay, over 2 sigma squared, okay, and this is normalized by 1 over square root of 2 pi sigma squared. So you should always remember this form here, because this form of the Gaussian is telling you a bunch of things about the qualitative form of the Gaussian. So we have here, for example, the Gaussian is going to behave like this. Okay, so we have some bell-shaped form. Okay, this is the Gaussian form. This is decaying like e to the minus, okay, x minus x 0 squared. Okay, so it's a very fast decay, this tail here. And so this is 2 sigma squared, okay? And the width of this Gaussian is going to be associated with sigma, okay? So this is, for example, this will be the spatial coordinate, and this is going to be the average position. The position of the peak is associated with this variable here, and the width of the Gaussian is associated with the sigma here, okay? So we can just read off from this solution here what's going on with the Gaussian. So we see that this is going to be the x0, okay? This is going to be here 2 sigma squared. So we can already write very easily what the average position of the Gaussian is going to be. So this is going to be mu p e0 t. Okay, so you see that this width is going to be not the width, the average position here is going to be moving as a function of time, and it's going to be moving linearly with time, while the identification of this is 2 sigma squared is 4 dp, so let's write that. So 2 sigma squared is 4 dp times t, implies that sigma squared is going to be 2 dp t. And as we know that the definition of the variance is going to be x minus x0 squared, okay? The average of this, okay? And so we see that x minus x0 squared, now the second here, okay? Okay, the square root of this is going to behave as 2 dpt square root. Okay, so we see that the sigma is going to be proportional to the square root of t. Okay, so the width, while the average is going to move linearly with t, the width of this is going to be opening up as the square root of t, much lower than the propagation rate. So all these things we should be able to verify in the experiment. We see that in the experiment when we see the pulse, okay, the pulse is going to be opening up and translating with a certain rate that depends on the properties. Okay, let me see what did I write this. Yeah, okay, so we know how fast it's going to move. It's going to depend on the applied external electric field, the mobility associated with the semiconductor, and the width is going to depend on the diffusion. So this, you see that the motion of this Gaussian is going to move according to the mobility, while the opening up of the bell-shaped curve is going to move according to the diffusion constant. So we can obtain, doing these measurements, we can actually obtain what these variables are going to be and compare them to the particular semiconductor and verify whether this ambipolar theory is working out. Okay, so from here we can verify ambipolar theory. Okay, because we can make these diffusion measurements, for example, from gradients of an electric field. We can verify what this diffusion constant is, and we can, if just from regular transport experiments, the conductivity measurements, we can verify the mobility, and then we can compare and see whether our ambipolar theory is correct or not. Okay, so is this clear? Any questions about this? So here we have a really close, a very neat closing to the problem of ambipolar transport. Okay, so it generates the physics of the excess carriers, and we now have an experiment where we can verify all these things. Okay, and to see how good our approximations are. Okay, one detail that we have left out from this equation is this guy here, okay? We're going to now determine very quickly what this tau is going to be in terms of the intrinsic properties, right? So for us, this is a sort of a parameter here, okay? Parameter here that we have to determine in some way. Let's see here, it would be in this pre-factor, this pre-exponential factor here. So this, we've described the physics of this Gaussian here, but we have this pre-exponential factor that tells me about the recombination rate. And let's see what the recombination rate should be as a function of the physics of the system, okay? So what is tau p? Okay? So this we will call the dielectric relaxation time. Okay, so this is a very easy application of electrodynamics. Okay, so in order to determine tau p, we just write down essentially the three EM equations that we need to solve. So one of them is going to be the divergence of E, which is going to be in the international system of units that we're going to review a bit in a short while. So we have the diversion, the Poisson equation, okay? With a G instead of a Q. Poisson equation. Then we have our relationship between current density and the electric field, okay? Ohm's law, okay? And then we have the final Maxwell equation we're going to use, which is the divergence of the current density is equal to the time change in, so this is the continuity, not a Maxwell equation, but the continuity equation. Okay, so if we have now this this set of equations, and let's assume that we have, and of course you can do this with the other assumption that the the charge density is due to positive carriers, for example. Okay. Okay. Remember, delta P is equal to delta N. Okay. Whatever. This is the basic assumption of these excess carriers, that we're bringing them across the gap of the semiconductor. And this will be a charge density that's going to be confined to this pulse-like generation of excess carriers. Okay, so let's just massage these equations a bit. So we can start with the first equation. So if we take with the Ohm's law equation, so if we take the divergence, okay, Ohm's law, let me put here, Ohm's law, we take the divergence of the current density of, from Ohm's law, and we will get this equation here. Okay, so take the divergence of that, and now we can write now using the Poisson equation, the divergence of E is determined, so this would be rho, sigma times rho over epsilon, okay? So now we have a relationship between the divergence of the current density and the basic parameters of the problem. We have the charge density, the electric constant, and the conductivity. And then we just plug this into the continuity equation. So we have that sigma, okay? Now continuity, sigma times rho over epsilon is going to be equal to minus d rho dt. And now we have this very simple equation to solve, okay? So we have d rho dt plus sigma rho over epsilon is equal to 0, okay? So this is a variable separation problem. So you put all your densities on one side and the time dependent on the other side, okay, on the differential, the differential of time, okay. This is just has a single type of derivatives here, which is a time dependent. So we can substitute this partial differential by a total differential. Okay, and we solve this equation by separation of variables. Okay, separation of variables. Okay, just in case you don't remember, so we have dp d rho over rho here. We'll have minus and then sigma over epsilon dt. Okay, and we integrate both sides of the equation. Okay, so this yields rho is equal to some rho at time 0, because this is just a first order differential equation, so we just need an initial condition times t over tau. I put a p, but this is just the solution to this. Okay, so this will be the solution. So we have that the evolution of the charge density is going to be like this is going to be just an exponential dependence. And remember here that I'm going to, from the differential equation, we just get minus sigma over epsilon, okay, times t. So we can identify now that the characteristic time with which this will decay is going to be 1 over tau. It's going to be, or let me write tau directly. It's going to be tau equals to epsilon over c. Okay, so this is going to be the dielectric the relaxation rate. So it's proportional to the dielectric constant divided by the conductivity. You see that now we have this recombination rate associated with the dielectric phenomena. It's going to be related to obviously to the dielectric constant and the conductivity of the system. So if the conductivity of the system is higher, then we have a more rapid, a shorter time for the relaxation, okay? And if our conductivity is very small, then this time is going to be larger, so the recombination rate is going to be a function of these two intrinsic material properties, again, associated with the semiconductor, okay? So this is a very nicely illuminating exercise, okay, of applications of electromagnetics to the semiconductor system. Yes? Anyone have a question?
Yes. How are we sure that rho is
Can you speak up, please? I can't hear you very well.
how do we know that rho does only depends on time?
How do we know that?
The rho.
The draw.
Rho.
What? The what?
the charge density?
Yes, only
How-
depend. How do we know that it only depends on time? No, no. The thing is that the charge density is not. It's remember that here in general we're going to we have to solve this differential equation. So the charge density can depend on space and time. The thing is that we just trying to derive the physics associated to this term here. Okay. So in principle, our system has to obey electrodynamics, okay? So this is just a statement. You see that here we also have spatial dependencies, okay? But they're being taken into account, so we can have gradients of the electric field and gradients of the current, the divergence of the current, so we can have current sources, for example, and these are going to be all associated with the excess charge in the system through these two equations. So this only is addressing the local dependence, the local relaxation rate associated with this term in the differential equation. So we're just looking at this, what this local term here is doing. So the rest of the charge dependence is going to tell me how charge goes into a particular volume and relax, okay, or goes out from that particular volume. So this is all taken into account here, okay? This is just a consequence of a dielectric relaxation at a particular point in space. And you see that those equations contemplate gradients, changes in space and time of the charge distribution, okay? So those things are taken into account. Okay, so let's draw some numbers, some numbers here, some numbers. Okay, and I'll make a small interlude related to the units we're going to use. Okay, so let's first do the exercise. So for N-type silicon, so this is silicon with a donor dopant. Let's suppose we have the donor density associated with this is going to be 10 to the 16, okay, centimeters to the -3, okay. So this is a number. Remember, this is a number density. Just so let's review those concepts while we do the exercise. So this is a number of donors per unit volume. So this has the units of cubic centimeters, inverse cubic centimeters. Okay, so let's calculate, for example, the conductivity, okay, associated with the silicon, N-doped silicon. So we have that, we have the mobility associated with the negative carriers times the number of dopants here will be the conductivity. Remember that we're just substituting the density of negative carriers by the number of the number of donors, which is there will be mostly the same if all the donors are ionized. Then this is going to be much larger than the number of carriers that are generated by thermal excitation across the gap. Okay, so this is going to be now with this number, knowing the mobility of silicon. Let us do that calculation. So we have here, this is going to be the electric charge is going to be 1.6 times 10 to the 19 Coulomb, which is going to be one of the units we're going to use in the international system. Okay, international system of units. Okay, international system of units. Okay, expect you haven't seen this quantity since maybe Common Core Physics or your electromagnetics course. Okay, so and this then we multiply this by the mobility. So we look this up. This mobility we look up in a table. So 1200. The units are going to be centimeters squared over voltage times seconds, okay? Voltage seconds, okay? That's the unit of mobility. And then we have 10 to the 16 centimeters, cubic centimeters, inverse cubic centimeters, okay? So those are the three quantities here. So if you calculate this, this is going to be a 1.92, and let us put all the units. So this is Coulomb times centimeter squared, voltage second, and then we have 1 over cubic centimeters. Okay, so we get this crossed out with this. Okay, and then we get this is going to be a Coulomb over second, and that's ampere, so this will be amperes over voltage, okay? And amperes over voltage is going to be in units of 1 over, I'm missing centimeter times centimeter, okay? And this is going to be in units of amperes over voltage, has units of inverse resistance. I'm going to review that in a second, times centimeters. Okay, so that's going to be the unit of our conductivity. Okay, so that will be the conductivity. That's one of the ingredients we need to calculate the relaxation time. And then the other thing we need is the dielectric constant. So remember that the relaxation time, that we remember here, the relaxation time is going to be epsilon over sigma. So we already calculated sigma. Okay. And now we need to calculate the dielectric constant. So the dielectric constant for silicon is going to be this prefactor here. This is one way to do it. So to write a prefactor, which is just a number, times the permeability, the permittivity of the vacuum. So this is going to be for silicon, 11.7, okay? This is just a numeric value, times 8 times 85.85 times 10 to the 40 to the minus 14 farads, okay? The capacitance unit over centimeter, okay? Faradays. Okay, so we do this calculation here, and so we get then, just by dividing these, the dielectric relaxation time for this situation is going to be an astonishingly small number, 539 times 10 to the minus 13 seconds. Okay, so this is a very, very quick relaxation. Remember, if you can refer to any time, for example, this would be, this time is much shorter, for example, than the time associated with the clock of your computers, which is in the gigahertz range. So this is 10 to the minus 9 to 10 to the minus 12 pico. So this is 0.539 picoseconds. This is really, really fast how these carriers are relaxed, are recombined in a semiconductor, okay? So very, very, very fast. Okay, so just you have these orders of magnitude in your head, but let us recall some issues about the units, okay? So the international system uses meters, okay? It uses kilograms, uses seconds, okay? For force, okay? It uses newtons. For pressure, again, not that we're going to use pressure much here, but just so that you know, pressure. Now everyone's using this. I remember when I studied, the CGS system was very popular, but then it was discontinued. Pascals, the charge, Coulomb. So this is this systems of units is generally dominated by the chemists. So the chemists like to change units a lot. I don't know why, but then, okay, so some units are very useful. So some things, for example, in the CGS system, the Maxwell's equations were particularly simple, but then now we have to put all these permittivities and permeabilities inside the Maxwell's equations in order to conform to the international system, okay? So we have coulombs, energy, okay? Energy in joules, and so on. Okay, so it is useful to see what everything, all the units that we're going to be dealing with in semiconductors. So we have, for example, resistance is going to be a derived quantity. Okay, so the resistance has units of ohms. Let me put here units. Okay, and here relations. Okay, so ohms is going to be defined, remember, by the ratio of voltage in the international system divided by amps. Okay, remember that this the relationship was I times R is equal to V. Okay, so if we divide voltage by current, we get the resistance. So that this is the basis of this ratio that I have here. Okay, conductance. Okay, as I'm a theorist, it was only a shorter while ago that I discovered this the new name for the units of conductivity were the Siemens. Okay, so this is amps over voltage, just the reverse of this relationship here. So this is related to the G times V is equal to I relationship for the conductance. Okay, this is the resistance. Okay, then we have the capacitance, which we're going to see issues related to the capacitance of, for example, a p-n junction. So this is the farad. Okay, and this is the ratio of charge to voltage. Okay, magnetic flux. Okay, so this is going to be the Weber. Okay, it's abbreviated like this. This is abbreviated like F. Okay, Siemens. Okay, and then we have this is going to be voltage times second. Okay, and besides this, we have some parameters that are going to be, of course, always the same, which is the Coulomb charge, 1.6 into the minus 19 coulombs. Okay, and the permittivity of vacuum, okay? The vacuum value, which is then going to be moderated by this prefactor depending on the material, okay, is going to be 885 times 10 to the minus 14 farads centimeter. I wonder why they use centimeters here if the official unit is meters, okay? But they use centimeters here. Okay. So these are the units that we're using in order to obtain this very, very fast decay in seconds that are coming into the equation. So you see that the relaxation rate is, at least in reference to some quantities that we know of in our daily lives, okay, which is, for example, the clock of a computer, which we know is always in the frequency range. So so if we have a computer clock, okay, so you have a frequency which is going to be a 1 over your oscillation period, okay. So if you have gigahertz, so 10 to the 9 hertz, okay, this is going to imply a 10 to the minus 9 second cycle, okay. So you see, even the fastest computers we generally have are going to be have very, very long cycle times compared to the recombination rate. Okay, so of course this is good because if you're using semiconductors in making a chip, you want any relaxation rate that you have to be much slower, much faster than your clock speed, so that you're running a steady state system, right? So any relaxation rates in semiconductors, okay, much faster than this. So this implies, and so our computers, okay, computers run in a steady state. Okay, if not, imagine if the clock speed then was much faster than this. If we try to do it much faster than the relaxation rate of our dielectric, then we would have the computer, each time it does a cycle, the semiconductor looks differently because it has a charge distribution that hasn't relaxed yet. Okay, so that's not a convenient setup for technology. Okay. Okay, so any questions about this? This is an important design feature that we have to take into account. Okay, so there's let's see, a couple of details we have to address before we get into the generic situations that we're going to have. So let's discuss briefly the quasi-Fermi level. Okay, so the quasi-Fermi level is, remember that the Fermi level is something that that is a fixed feature. Okay, so the Fermi level is an equilibrium feature of semiconductors. Okay, that is, you remember that we have this situation here, this generic situation. We have the valence and conduction band. And if we have no impurities, right? So we will have the Fermi level, will be the intrinsic Fermi level, and will be right in smack in the middle of the gap. Okay. So as we, for example, let's suppose we start adding here now dopants. Let's suppose they're going to be donors, for example. Then we add the donors here, and then these add electrons up here, okay? So we have to account for the excess electrons that are going to be here due to the impurities that this Fermi level is going to move. So imagine that we can do this as a function of time. So we start adding dopants and we start adding negative quantities. So we start shifting this Fermi level up, and it will end up in some place around here. Okay, so we'll have that. Our Fermi level is going to be here. Okay, and this is going to be then after I stop adding dopant, then this Fermi energy is going to be shifted, and then it's going to stay there as a fixed quantity for our system. Okay. There's a similar feature, a similar argument applies for if we add acceptors here, okay, and then this Fermi level will shift down in comparison to the intrinsic Fermi level, okay. But what happens now if we, what happens, don't like writing in green, what happens if we add excess carriers, okay? And we know that these excess carriers only live for a certain time and then relax, okay? Then intuitively, if these excess carriers are of the negative type, okay, they're going to be both we're going to have the same number of both types. But if we add an excess negative charge, then this Fermi level is bound to move about in time. Okay, so we're going to have a quasi. Okay, what happens if we add excess carriers? And let me put here the implication. We have a quasi Fermi level. Okay, so how do we describe this? Then what we need is that then the excess carriers, okay, n is going to be, for example, n0 plus delta n, okay, and we know now we use the relationship that we had for the equilibrium carriers, which is going to be the intrinsic concentration times now in quasi-Fermi level associated with the excess carriers now referred to the intrinsic Fermi level. Okay, so that's what we're going to have, and the same relationship for P going to be P0 plus delta P equals to the intrinsic carrier concentration. Remember that when we have excess carriers. Okay, when we have excess carriers, it is not true that n times p, okay, is equal to ni squared. Okay, this is not when we have excess carriers. Okay, while we know that n0 times p0, where these are the equilibrium, okay, the thermodynamic densities of carriers is equal to this, no matter whether we have doping or not. Okay, so from these relationships, we can now solve for the the quasi-Fermi energy. So just taking the log on both sides of this equation, we have that the quasi-Fermi energy for negative carriers referred to the intrinsic energy is going to be the log of n0 plus delta n, okay, over the intrinsic concentration, okay, times kBT. Okay, so let's quickly do an exercise with this, putting some numbers into these relations. So let's suppose we have, let's suppose we have temperature is going to be 300 Kelvin, okay, and we have an N-type semiconductor, okay. Okay, and let's suppose so we have an N-type, we have N0, 10 to the 15 cubic centimeters, inverse cubic centimeters, and we have an intrinsic concentration of 10 to the 10. Okay, then we should have a P0. We can determine it from this relationship here. So this will be N0, and this will be then 10 to the 5, just by the ratio between these two quantities. So this is going to be in this cubic centimeter. Okay, and let's assume now, okay, that we have an excess carrier concentration, which is delta N equals delta P equals 10 to the 13. Okay, so if we put in equilibrium, okay, in equilibrium, we're going to have the Fermi energy. So we can identify where the Fermi energy is going to be for this combination. So this is going to be kBT log of 10 to the 15 divided by 10 to the 10. Okay, and we cancel units here, and this is going to be 0.2982. Okay, and this is going to be in electron volts. Okay, I know this is not the unit of energy, so this is one of these schizophrenic features of this area. So generally, we would like to write this in terms of joules if we were in the international system, but you know, physicists like electron volts a lot, so we write this energy in terms of the electron volts. So that just refers to the unit we have to use for the Boltzmann constant, okay? And the temperature units are always the thermodynamic units, okay? So this we can write in terms of the electron volts if we write the Boltzmann constant in terms of electron volts, okay? And finally, if we add these impurities out of non-equilibrium, which is adding adding these excess carriers, we'll have that EFN minus EFI, which is going to be the intrinsic. So this is always going to be a reference in the middle of the band. So this will be kBT log of 10 to the 15 plus 10 to the 13, okay, over 10 to the 10. All these are in centimeters, cubic centimeters inverse, which get cancelled. And this gives me 0.29. So this is going to be really small, as you can guess, 4 electron volts. Okay, so the image here that we have, the scenario here is that we have the valence and conduction bands. Okay, so the intrinsic level is going to be here, I. Okay, this is going to be the Fermi level let me put it in black. So the Fermi level is going to be here for the equilibrium, okay, without excess carriers. And if we add these excess carriers, then we're going to have a new Fermi level. Let me put it like this here. Okay, and this is going to be the quasi. Okay, so if we put now the quantities here, this should be this separation here is going to be 0.2, 0.29, 0.2982, and this is going to be 0.29. So if we, of course, if we add delta n, this gets shifted upward a little bit, and we get an intrinsic Fermi level which is shifted up. Okay, this is very simple. We could also calculate, for example, the EFP. Okay, and this will give me another level here, which will be now in the below the intrinsic level. It will be something like this. Okay, and this will be a smaller quantity, although this quantity essentially doesn't exist in equilibrium semiconductors, which will be this quantity here, and it will be 0.179. Okay, and this will be the Fermi level for the positive carriers. Okay, so let's stop here, and we'll continue tomorrow doing some. Okay, so tomorrow examples. There's some emblematic examples of ambipolar transport. Okay, any questions? No, you have to run to the next class. Okay, so see you tomorrow then.
Bye, teacher.
Bye bye.
See you.
See you. Bye bye.